I'm Dr. Roger, and today we're looking at differential equations, in particular systems of linear differential equations. I'm looking at x prime equals ax, where matrix A is 1, 1, 4, 1. And to solve this, we're going to find the eigenvalues. Which we do by setting determinant of A minus lambda times the identity equal to 0. So A minus lambda times the identity will give me 1, 1, 4, 1 minus lambda times 1, 0, 0, 1 equals 1 minus lambda, 1, 4, 1 minus lambda. And the determinant of that matrix is 1 minus lambda, 1, 4, 1 minus lambda determinant, which is 1 minus lambda times 1 minus lambda minus 4 times 1. The product AD minus BC in the matrix ABCD, and that equals 0. FOIL gives me lambda squared minus 2 lambda plus 1 minus 4 is minus 3 equals 0. Factoring lambda and lambda, 1 and 3. The 3 is negative and the 1 is positive. This product equals 0, so either the first factor equals 0, lambda equals negative 1, or the second factor equals 0, so lambda equals positive 3. I'm going to call these lambda 1 and lambda 2. Now that I have eigenvalues, I want eigenvectors. To find my eigenvectors, I solve A minus lambda times the identity times, I'm going to call it vector xc equals the 0 vector, where the vector xc is just using the Greek x for this because tradition in several textbooks that I like. So A minus lambda I is this matrix as matrix, well this one really, putting lambda 1 equals negative 1. And I get 1 minus negative 1 is 2. 1, 4, 1 minus negative 1 is still 2. Times xc1, xc2 equals the 0 vector. Those rows are multiples of each other. So the first one gives me 2 xc1 plus xc2 equals 0. And the second one gives me the same equation, just multiplied by 2. You cannot find a unique solution, but we can choose a value. xc1 equals 1 is often a convenient value. That gives us 2 xc1 is twice 1, and then plus xc2 equals 0. Twice 1 is 2, subtract that from both sides, and we get xc2 equals negative 2. So our eigenvector 1 is 1, negative 2. You can multiply that by any constant you wish. So if we had chosen xc2 equals 1, xc1 would have been 1/2. That's multiplying xc1 would have been negative 1/2, multiplying each component of this vector by negative 1/2. Your eigenvector is unique up to multiplication by a non-zero constant. For our second eigenvector, associated with lambda 2 equals 3, A minus lambda I is 1 minus 3 is negative 2. 1, 4, 1 minus 3 is still negative 2. And that times xc1, xc2 equals the 0 vector. And again, the second row is now negative 2 times the first row, so they give us the same equation. Negative 2 xc1 plus xc2 equals 0. If I choose xc1 equals 1, then negative 2 times 1 plus C2 equals 0. So negative 2 plus C2 equals 0. C2, the second component of my C vector, is positive 2, and eigenvector 2 is 1, 2. Our two solutions are solution x1 equals e to the lambda 1 t eigenvector 1, which in this case is e to the negative 1 t times 1 negative 2. And x2 is e to the lambda 2 t times eigenvector 2. It's important to give your eigenvalues and eigenvectors subscripts so you keep them paired with the correct one. And this is e to the 3t times 1, 2. Our general solution is x equals c1 times your first solution plus c2 times your second solution. With larger matrices 3 by 3, you'd have plus c3, x3, etc. So in this case, c1 e to the negative t, 1 negative 2, plus c2 e to the 3t, 1 positive 2. If we substitute that in, we can confirm that it works in the original equation, and I'm going to do that. So I'll just test each solution separately. x1, distributing the exponential into the vector, is e to the negative t, negative 2 e to the negative t. x1 prime is the derivative, negative e to the negative t, and positive 2 e to the negative t. Let's look at ax1. That's 1, 1, 4, 1 times e to the negative t, negative 2 e to the negative t. So that's 1 e to the negative t minus 2 e to the negative t is negative e to the negative t. And 4 e to the negative t minus 2 e to the negative t is positive 2 e to the negative t. If you try that with x2, our second solution is e to the 3t times 1, 2 is e to the 3t, 2 e to the 3t. And x2 prime, the left-hand side of x2 prime equals ax2, is 3e to the 3t and 6e to the 3t. Our original equation, if this is a solution, that should be the same as ax2, and ax2 is 1, 1, 4, 1 times our x2 vector, e to the 3t, 2e to the 3t. And so that's ax2 equals 3e to the 3t, I'm sorry, 1e to the 3t plus 2e to the 3t is 3e to the 3t. And 4e to the 3t plus 2e to the 3t is 6e to the 3t. And we note that in this case, yes, x1 prime equals ax1. And in this case, x2 prime equals ax2. Therefore, x1 and x2 are solutions. Of x prime equals 1, 1, 4, 1, x. Solving systems of linear equations is a question of finding your eigenvalues and then the corresponding eigenvectors. This gets more complicated when you have repeated eigenvalues and when you have complex conjugate eigenvalues, and we will look at those situations also. Come back soon for my next video. With math, there's always more.